will be given by Sarvesh Ravichandran Iyer. I'm sure most of us know him. His research interests include Levy process and stochastic differential equations. Today's talk will be on.
Well, it will be on convex sets today, but tomorrow I'll also be talking about convex functions, and we'll try and discuss some concepts that come from the basics, but which rise up to the current research level in the study of convex sets and functions.
Okay, over to you.
Yeah. Gautam Barani used to say that you are not a professional mathematician unless you have colored chalks of 4 different colors on your bench. So now that's 4, and including white, that's 5. So I must be a super professional mathematician.
Yeah.
Oh, great. I spent 3 hours practicing, 1 hour practicing. Right.
It's fine.
Yeah. Okay. So, in mathematics, when we define things, we generally desire 3 things. So, what are these 3 things that we desire when we define or introduce various mathematical notions? While introducing notions in math, we typically think of 3 things. The first is their naturality or their usability. So for example, I would want to try and model something that's next to me. So there is water bottle. I would like to understand perhaps something about this water bottle. So I would define a set that perhaps looks something like this water bottle or that one. Or this iPad here looks like a rectangle, so I would naturally want to study rectangles. Or this chalk which looks like a cylinder, so I would want to study cylinders for example. Or you look at puddles in nature, for example, after the rains. So there is a reason why we define mathematical notions, and one of them is naturality or usability. What usability means is that you don't observe things as they are, you perhaps observe them as they evolve. So for example, you are modeling traffic in a city or something like that. So for that reason you want to consider a graph, something like that. So usability also comes down to naturality because it's about how often a certain phenomena or a thing occurs in real life, right? Now, along with naturality and usability, there's also ease of use. How easy is it to understand? Is it too difficult to understand? Is it too complicated, too hard to work with? Or is it something so simple and ordinary and easy to understand, which is like so durable and you can sort of move it around and easily generalize it? So, ease of use and naturality are 2 things. The third is something that I have forgotten again. The third of these yes, the third of these is something pretty obvious. The third of these is just aesthetic. Aesthetic, right? Things are beautiful. You define things like fractals, for example, because they're beautiful. I mean, a fractal has certain symmetries associated with it, and you find those things beautiful. So you want to define something like that. Perhaps someone on a fashion show is trying to model how women look, or something like that, or should look, so that they win the pageant. And they are able to design dresses on the basis of that. In fact, recently there have been some applications of graph theory and so on to the way fashion designers have designed clothes, and that has to do with aesthetic beauty. So we generally for these three reasons, we typically define mathematical constants. Now, we need to think about why convex sets should be defined. So why should convex sets be defined? Do they kind of fit all these criteria in some sense? The answer to that is somewhat yes. So for example, when you look at naturality or usability, you think of so many objects which are rectangles and circles. Rectangles, my iPad is a rectangle. Circle, my face looks like a circle. I think my face looks like a circle. For example, right? Dot, dot, dot. So many things in life look like convex sets. What about ease of use? Well, ease of use is not a problem actually, because as I've been showing you, convex sets are extremely flexible. You can move them around and they'll still be convex. You can stretch them and they'll still be convex. So, if you turn out that this is true, now this is true, whatever true means. True means well good enough to choose a meaning. And aesthetic beauty is well, I don't know, you guys like rectangles, circles, polygons. I mean, we've all been working with polygons like these and or these kind of, puddles, ellipses and so on. You've been seeing them here and there, right? And for various reasons, both symmetric as well as the sort of ease with which they are constructed, the naturality with which they are constructed, they are beautiful as well. So for this reason, convex sets are defined to fit these criteria. And now we will come to the definition of a convex set. And before coming to that, I need to put through some notation for you guys, which will be thankfully fairly simple. Because this talk has been designed with the average first year student in mind. And because of that, there won't be too many complicated distances, there won't be, I don't need to raise my leg and do various kind of mudras. So it's just basic stuff, basic ordinary stuff. So for example, we have the real line. So just think of the real numbers as they are. So there's no need to know any kind of formal construction of the real numbers. The real number line, great, fantastic. Okay. Now after you know the real numbers, you have the sort of tuples of real numbers, which are so-called Rn, as they like to say. So if you have a number n greater than or equal to 1, you can define Rn as just tuples of real numbers. x1, x2, x3, up to xn. Where each xi is in R. Right? So for example, this board is a subset of R2. Because if I think of a coordinate plane, every point here can be written as an x coordinate, say 2 or something, and a y coordinate, say 3 or something. So that's the way to think of Rn. High dimensional space, in some sense, is how you should think of Rn. Now once you have Rn has some very natural things associated with it. So what are those natural things? There is an addition on Rn. There is an addition on Rn. That's just component wise. So for example, what is x1, x2, x3, xn plus y1, y2 up to yn? Well, it's just component wise. x1 plus y1, x2 plus y2, and so on until xn plus y2. Okay? So there is an addition on Rn. Then what else is there? There is a scalar multiplication on Rn. There is scalar multiplication on Rn. So what does that mean? If you have an element, like let's say, I don't know, if you have say x in Rn, you can multiply it with any c in R and get something like a cx in R. How do you do that? Yet again, that goes component wise. So c times x1, x2 up to xn is just cx1, cx2, cx3 and so on until cxn. So there is a scaling available, there is an addition available, and these guys, there is some relationship between them. Obvious stuff like 2 times x is x plus x. Obvious stuff like that. So that's just distributed. So now what else is there? There is a norm on Rn, right? If I take any point on Rn there is an origin in Rn, by the way, which is just a point 0, 0, 0. So this 0 that you see here is just a point 0, 0, all coordinates 0. And this is the point that I call as the origin in time. This is called the inequality. Okay? To practice writing in both hands. Anyway, so the distance from the origin can be taken in a Euclidean sense. So what does that mean? That means that you operate according to Pythagoras' theorem. If you are calculating the distance between 2 points, you want to find the distance of this line segment. So you create this right triangle and use Pythagoras' theorem. And the thing is, you can do the same thing in high dimensions. You can do the same thing by creating multiple triangles in high dimensions. And so basically speaking, by Pythagoras' theorem, you have a distance between points. You have a distance between d of x comma y, which can be defined as square root of summation 1 to n xi minus yi. So this is there. There is a distance available, and associated to this distance, there is a norm available. So norm of x is nothing but the distance from x to 0, which in this case is therefore square root of summation x I equal to 1 to n. Okay. So this norm and this distance and so on, they are just defined and they are going to stay the same. These guys are going to stay the same across both lectures. I am not going to change the distance. We all know from previous talks that there are many distances available, but I am not going to change this distance. This distance is very fundamental to what I want to do, right? And once we have these guys, we have the balls, right? So what is a ball? A ball is literally what it is. It's a ball shape set. So for example, whatever this is a ball. Now every ball can be characterized by a center and by a radius. So a center and a radius. So how is that denoted? It's denoted by the following, and that B center radius is the set of all points y such that the distance between C and y is less than. So please watch out for this line. This is less than. So that means the boundary of a ball is technically not part. So it will be like the ball will be up till radius r, but not including radius. It will be like this. It won't include the boundary, right? So now we have, I think we have everything we need to go ahead. And now I can define what is called a convex. Yeah, that's right. I can define what a convex is, right? So in order to define what a convex set is, I need to first define two very obvious geometric objects, namely lines and line segments. So given x comma y is Rn. So let's say this is x and this is y. This is y and this is x. The line joining x and y is this entire line. On the other hand, the line segment will just be this part. So this will be the line, but this entire thing will be the line segment. This small thing will be the line segment. And when you see how I define it, you will understand clearly why it's like this. So given x, y in Rn, you have the following subset of Rn, which is called as Lxy. And this is what? This is just the set Ex plus 1 minus Ey, where E runs over all real numbers. So what you're doing is you're capturing everything between x and y, but you're also capturing everything on either extreme. That's why you're letting E run over R. And this is called the line joining x and y. Not the line joining x and y. This is the line that is created by x and y. And now you have this notation, which I have borrowed from a book. If somebody asks me for the references, I have provided it. This notation is the notation for the line segment between x and y. So now what is the difference between these two sets? 1 minus Ey, where E only belongs to 0. closed 0, so you are including T0 and you are including T1. So that X and Y are included in the segment. So X and Y are both included in the segment, and everything in the middle is kind of included here. So this is the line joining X and Y. This is the line segment joining X and Y. Right. Now we are ready to define convexes. And along with it, a sister notion which generally precedes it called an affine set. So, definition. A set, let's call it A, set A subset of Rn. By the way, in these n can be anything, n1, 2, 3, n2. But later on, for the purpose of convex functions, because multivariate differentiability is not known, I will go with n equal to 1 because their differentiability is well known. A set A in Rn is called affine AFFINE if for all xy in A, the entire line segment joining x and y is actually contained completely. And it's called convex if for all x comma y in A, just the line segment is contained. Any doubts? Must, sir? Good. So now we have an idea of what convex sets look like. We should first though have a discussion on affine sets. So the point is that if you, without having a discussion on affine sets, it makes no sense to talk about convex sets. I mean, okay, should not say it makes no sense, but it motivates convex sets far more than anything else does. So let's talk about it. Well, if you think about an affine set, let's take 2 points. Let's draw 2 points. Suppose these are 2 points of an affine set. That means this entire line segment is contained. Okay? This entire line segment will also be contained in A. Now, if I have another point here, which is also part of A, then see what happens. What will happen is, this line segment will also have to be a part of A. This line segment will also have to be a part of A. But then we've created all these line segments here, and now this will have to be a part of it. Then you take these 2 points, these 2 will have to be a part of it. And at the end of the day, when you keep doing this, you will realize that the entire plane will have to be a part of A. So what happens is that, so the way to think of an affine set is that it has a lot of regularity. So what are examples of affine sets? I mean, obviously I should give an example of an affine set. Well, an obvious example. Of course, Rn is affine. It's so obvious, right? Then, of course, the empty set. I'm not even going to mention the empty set. Well, a single line segment is affine. A single line segment is affine.
Isn't it this line?
Oh, sorry? A whole line, a line. Like, for example, if this is the coordinate plane, then this entire line that you see here, which is probably what y equal to 2 or something like that. So y equal to 2 will be a affine set, for example. And so will something like this, x equal to y. X equal to y will also be an affine set, for example, right? So affine sets are basically sets such that when 2 points are in it, the entire line segment is in it. Entire line. I'm sorry. I keep confusing the numbers. Thank you very much for the interruption. Right. So you have Rn, you have lines, and then you have these so-called translated things that I just showed you, right? You have these kind of tilted lines, so to speak, right? Like x equal to y, or the y-axis, or x-axis, or anything like that, right? You can take something away also. For example, it need not be necessarily adjoined to the other. You can take it here. Even this would be another affine set. Right? Now, here, there's something very interesting. Remember I talked to you about how an affine set ends up sort of covering everything. Like, if just 2 points are in it, or just 3 points are in it, it somehow turns out that it ends up covering like a whole 2-dimensional plane of sorts. It turns out that every affine set, every affine set in Rn, and anybody who has gone through one course in linear algebra will be able to easily get this, is of the form A is equal to mx plus b, where m is some matrix with n dimensions with real entries, and b is any vector. So basically speaking, anything that is the image of a matrix possibly translated by a particular vector. So for example, for this guy, the matrix will be some kind of rank 1 matrix, and the vector v which is translating it will be this vector. So every affine set is literally of this form, right? So the way to think of affine set is think of planes, lines, okay? And in this slide, I will be defining something called as a hyperplane. Just a minute. So these hyperplanes and half spaces that I will be talking about, they are going to be very integral to the theory of convex sets, because they still are. I mean, there's still research going on in, for example, higher dimensional spaces in this Rn as to how one can understand, separation theorem and so on. Right. So now we are going to define what is a hyperplane. But before that, let me literally draw a hyperplane for you, right? So what is a hyperplane? Let's say I am in 3 dimensions. Okay. If I am in 3 dimensions, any 2-dimensional plane is a hyperplane. So for example, let's say I am being cut in half by some kind of sword thing. That is a hyperplane. So if it would look like this, right? And for example, let's say this, I am using this iPad. This iPad will create a plane, right? It will create a plane. If I tilt it a little bit, it will still continue to create a plane. So all those guys are hyperplanes. And how do you characterize hyperplanes? Well, you characterize them in the following way. So definition of hyperplane and half spaces. Well, half spaces are, it's literally going to be obvious to you what it is mean, but I'll mention it again. So if you are given a vector v in Rn and you are given a real number v in R, then this set H, which is given by all x such that there's a dot product. In my introduction, I forgot to mention a dot product, but x dot v is equal to v. Is anybody here not sure of what a dot product is? Please let me know. Dot product is okay, right? Okay. So x dot v is equal to v. So you collect all vectors such that their dot product with a particular fixed vector is equal to a particular number v. This is called a hyperplane. Now, anybody who's done linear algebra will instantly understand this definition. You can write H as the kernel of a linear transformation of rank n minus 1. So that's why, as the kernel of a rank 1 linear number. So this is called as a hyperplane. And now, what happens when you have a hyperplane? So let's say you have a hyperplane like this, right? So this is in 2 dimensions, and this is a hyperplane H. Now, when you have a hyperplane, it divides the space into 2 parts. There is one part here, which is H1, and there is one part here, which is H2. And for the purpose of this talk, these hyperplanes will be assumed to intersect in H. So both of them will include H. But there are still 2 sides of H. One side of H, another side. And those sides are called as half spaces. So the sets which are given by H1, H2, no difference. 1 and 2 don't make a difference. You can just take the same. So it will be given by all x such that x dot v is greater than or equal to v. And you have H2 which is all x such that x dot v is less than or equal to v. These are called as half spaces. The half spaces are associated to H because H helped form them. So you have a hyperplane, it forms two half spaces that are associated to it. And now what we said before tells us that every hyperplane is an affine set. And in fact every hypersurface is also, yeah right, every half space will also be an affine set. Every half space will also be an affine set. So that's the point, right? And once you do that, we can now discuss some properties of these affine sets. Before we move on to convex sets and why we desire them, we should look at some properties of these affine sets. Right? So properties of affine sets. At this point, I am going to be very loose. Properties. So I'm going to put quotes here because nothing I'm saying here is mathematically equal. I don't get it. Okay? I'm just going to use some loose words that are going to characterize naturality, aestheticity, and ease of use. Right? What's the first of these? Well, when you draw a hyperplane or when you draw an affine set or something like that, you think about, let's say you think about a line. Don't even think about it. Think about a line. A line is uniform. It's uniform. What's happening here is also happening here. And what's happening here is also happening here. In what sense? In the sense of slope, for example. So the slope of the line here is the same as the slope of the line here, same as here, same as here. So a line literally has uniform slope. And if you notice, the same thing applies to the iPad. So for example, if I click the iPad here, then the slope at this point, upward, left, whatever direction you look in, is the same as at another point, upward, left, whatever you look in, right? So that uniformity in slope or gradient or whatever you would like to call it should be associated to a calculus related benefit of affine sets. So affine sets are good from a calculus point of view because they have uniform slopes and are easy to study from an analytic point of view, right? Now what's next? Because I had a certain order to it. I remember them but not in the order that I presented. Right. So we just talked about these matrices and these vectors and so on, right? From a linear algebraic point of view, this means that affine sets are easy to represent. So affine sets are easy to represent. So if I need to represent an affine set, I can just use linear algebra for that purpose, right? So I've already shown you that from a calculus point of view and from a linear algebraic point of view, it's convenient. Now I will be telling, now there are other good properties. So for example, what do you notice about a line? It's unbroken. If I cut this out, it's not a line anymore. It's not an affine set anymore. Similarly, if I have a plane and I chop off one point from it, it's not going to be affine anymore. So one of the important properties of these guys is some kind of connectedness, whatever that means. Whatever that means. I said it 3 times. Whatever that means. So this is from a topological point. If you are trying to understand from a topological point of view why these sets are desirable, it's because they're kind of connected in a certain way, right? And the fourth, and last but not the least, comes down to something you guys might have done in vector algebra. What happens when you draw a line and you have a point outside the line? Can somebody tell me how to find the distance from this line to this point?
Drop the perpendicular.
Exactly. To drop a perpendicular, right? So you find a point where this is perpendicular, right? And you are able to get the distance between this point and another point. Moreover, the relationship between this point and this point is interesting. The point is, this guy is the unique point which is closest to this. If you take any other point, say here, or here, or even here, say, the distance from that guy to this guy will be bigger. So if this guy is some D, this guy will be bigger than D. This guy will be bigger than D. Every other point it will be bigger than D. Let's say this is the affine set. Only this guy will be the nearest neighbor, satisfying that unique property. So this is, how would I summarize this? This is actually good for optimization. In the sense you can say good relations to outside points. Or you can even, I mean, for somebody who is a little more high level, you can call it as projective properties. So, outside points. So, this is good for optimization. You see how convenient affine sets are. They are not just things that you've thrown out and been like, oh, chalo, swallow them, like some mess food or something. Right? Uniformity in slope. Easy to represent in linear algebra exams. They are connected, they are good sets. And they are good in the sense that you can find the distance from any point to an affine set. Now it turns out that convex sets are going to carry a lot of this forward. So convex sets will keep the legacy. Convex sets carry this forward. Right? This is what we are doing. So now that we've seen the magic of affine sets, we should finally explore the magic of convex sets. And when I'm starting something about convex sets, it would be stupid for me to not give examples. So let's do that. So let's start with the obvious examples. All affine sets are convex. Affine implies convex. I'm not even going to say why. If anybody doesn't know at this point, you can still ask. But I'm not going to say. Okay, so affine implies convex. That means all your hyperplanes and all your smooth lines and whatnot, they're all convex. Next, what else is convex? Convex polygons. You take any 3 points or any 4 points, sometimes you can join them in such a way that they form a convex polygon. Right? So this or this square, any triangle is convex. Literally any triangle is convex. Any line segment is convex. So you have all these examples, and these guys, they have a general name. When you take these finitely many points, make them as vertices and kind of join them up in a convex way, it forms what is called as a polyhedron. So I'm not going to give a rigorous definition of a polyhedron here. I'll probably give it in the next talk. But roughly speaking, a polyhedron should be thought of as a high-dimensional polygon. For example, a 3-dimensional polygon is a cube. A cube is a polyhedron, for example. But a circle is not, a sphere is not, because it takes infinitely many points to determine it. So polyhedrons are, for example, a great example of convex sets. Then of course you have your circles and ellipses. Circles, ellipses, right? And these, as we know, they appear, for example, in coordinate geometry. In 2-dimensional coordinate geometry, they appear a lot. And of course, there are higher dimensional values like ellipsoids, spheres, and so on. And the thing is, these are natural. I mean, soap bubbles are spherical in nature. Footballs are spherical in nature, for example. Okay, footballs are not exactly spherical, but whatever. For our purposes, we can treat them as close enough. Right. Now let me come to a very interesting example. These are called as Fahrenheit cells. Let me quickly explain to you what happens in a Fahrenheit cell. Okay? So let's imagine we are all shopkeepers. I mean, okay, we all sell the same thing. Maybe we sell mathematics or something like that. So I'm standing here, there's one standing in that corner, there's a third person standing there. And let's say we're all equal in the sense that we're all not better than each other and not worse than each other. We're all the same. Now let's say there's someone standing there. How is he going to decide who he wants to come to? So one that's the closest, right? So now if I'm standing in a place and I want to find out who is going to come to me, that is my Voronoi set. If that guy wants to find out who's going to come closest to him, he has to find out who is closer to him than to anybody else, right? And that is his Voronoi set. Now what happens is, when you take any n points in the plane and treat each one as a shopkeeper, then each guy will decide for himself who are the guys who are going to come to him, or who are the guys who are closer to him than to anybody else. So then you will get some cells like this. You will get some cells like this. this maybe this something like that, right? And each guy will be captured in his own cell. Each guy will be captured in his own cell, right? So you have some cells here. Maybe you have a C1, you have a C2, you have a C3, you have a C4, you have a C5, and so on. These are called as Voronoi cells. This is pronounced Voronoi. Voronoi died of a stomach ache at the age of 40. His son was the first person in the world to perform a kidney transplant. Right. So yeah, probably academics does go into these. Anyway, so these Voronoi cells, there's a theorem, of course, the theorem of Voronoi himself. Regardless of how you arrange the points, these Voronoi cells are all going to be convex cells. So it's a theorem of Voronoi that you place the points anywhere you want. So place how many ever points you want. Place this x1, x2 up to xr points in Rn. There needs to be no relationship between n and r, apart from the fact that they are possible. And create Voronoi cells. So I'm not going to write down rigorously what this means, but it barely takes any effort to be honest with you. And by the way, what does closest mean? Closest is the Euclidean distance. So if somebody is measuring with respect to Manhattan distance or some other random distance, they get different Voronoi cells. But this theorem holds only for the Euclidean distance. In Euclidean distance. So this is very important because it turns out in high dimensional geometry and with non-hyperbolic geometry and so on, all these things just absolutely falls apart. So if you place these guys, then the Voronoi cells are common. And you see, this is an optimization problem. This is essentially the result of each person optimally deciding who is closest to them. So we've naturally obtained convex sets from an optimization problem. And this is why I wanted this example. This example is really good. So I think I'll take a small break, perhaps 5-10 minutes, and we'll continue. So there are two more very key examples that I need to express, but they're not particularly important. One of them is particularly important because you guys will see it soon enough. The other one you guys might see a little later. So let me go. Recording शुरू हो गया? Great. Now, how do we understand high dimensional objects? When we think of, let's say, image resolution, let's say you're a computer and you're trying to break down a high dimensional object. What you do, for example, is you try to understand it in small levels, right? Or what you try and do is you try and make it up, try and create it with the help of some very simple structures. So the idea of one part of mathematics called as Simplicial Homology is that you create approximate high dimensional random structures, not random, high arbitrary structures using simplices. And what are these simplices? Simplices are nothing but, instead of giving you a rigorous definition, which is going to take some time, what I do is I'll just draw some diagrams, right? So, zero-dimensional simplex is just a pointer. A one-dimensional simplex is just a line segment. A two-dimensional simplex is a triangle. A three-dimensional simplex is what happens when you put four lines together, four triangles together in a compact fashion, namely a tetrahedron. So a tetrahedron comes from putting four triangles together. The way of thinking, the way of understanding how to build these simplices is that you build a line from points, you build a triangle from lines, you build a tetrahedron from triangles, and now a four-dimensional simplex is going to build something out of a tetrahedron. It's going to stick tetrahedrons together and create a four-dimensional object, right? And these simplices, what's the idea of simplices or of simplicial homology? The point is, you want to understand a particular mathematical set by understanding how well it can be approximated by simplices. So the idea of so-called simplicial homology, so-called, which you learn much later, but which I'm just going across because I want to look like I know something more than this, is that such a brain person. Anyway, is that you break, quote unquote, break a set into simplices and understand its structure. Its structure. So right now I'm just going to leave it like this. But there is the point is that when you study simplicial homology, you'll see that the convexity of simplices comes for something. So these simplices are convex. If you see, this is a convex set, this is a convex set. If I fill in this tetrahedron, if I fill it in with water or something, that's a convex set. So these are all convex sets, and their convexity counts for something in simplicial homology, right? And
Is this somewhere related to the fact that, for example, when we are dealing with two-dimensional surfaces, we can sort of triangulate them?
Exactly. A triangulation of a surface is nothing but a way to understand it through two dimensions.
So, I have seen somewhere that this thing leads to a proof of the other characteristic for sphere.
It does. It's very simplest.
So, does this generalize also?
It generalizes. Yeah. Actually, it generalizes. Bushy make generalizes. And finally, the last are matrices. Convex bunches of matrices. Now the point is, I am still working in Rn. So you might be like, matrices kahan aa gaya? So now the point is, you don't think of matrices as, you can think of course you should think of matrices as sets with real number, not sets. I mean these boxes with real number entries, but they are also obviously members of Rn square. So an n cross n matrix, it has n square real entries. So just think of an element as an element of Rn square. And it has its own addition and so on, which is basically speaking the same addition as Rn square, just carried forward. Now you have here certain interesting convexes. So what are those? So one of them, which is a very obvious one and which I need you to find out, is just matrices with non-negative entries. So if you take matrices, all of which entries are non-negative, then that will be a convex. Now what you can do is, you can take not only matrices with non-negative entries, but every row adds to one. Every row adds to one. So what's an example of such a matrix? An example of the matrix is half, half, 1 by 3, 2 by 4. These matrices have a name. These matrices that you see here are related to Markov chains, which is a concept in probability, and on which I have actually given another talk in the math club seminars. And these are called as stochastic matrices. Stochastic matrices. So these stochastic matrices are another very important example. Are very non-trivial. I mean, for this level, I have to say. For those who are at third year and so on, it will be very straightforward. Is that matrices with symmetric matrices with all eigenvalues non-negative, they are also a convex. So that is a not so obvious fact, and because people are not aware of what eigenvalues are, I won't write it down. But that is another fact. So those are called as positive semi-definite matrices. Positive semi-definite matrices form a very important convex. And with that, we will now move to some properties of convex. Right? And now I'm going to say something very interesting. Just like how we have addition of real numbers, we can add sets. It turns out that there is a natural way to add sets. How do we do that? Let me quickly explain. Let me first make a definition. It's called as the Minkowski addition. So if you are given, let's say two subsets, omega 1 and omega 2, let's say that. you can define omega 1 plus omega 2 as the following step. You take every element in omega 1, every element in omega 2, add it together. That gives you some element, right? Now you collect all such elements. So W1 plus W2, where W1 is in omega 1 and W2 is in omega 2. Right? So this guy is a Minkowski addition. And now how do you think of Minkowski addition? What do I think of Minkowski addition? Let's see what happens when I add a triangle to a circle. So this is a circle and this is a triangle, right? So what is circle plus triangle? Think of it this way. What you are doing is you are taking each point of the triangle and literally pasting the circle. So you have the triangle here. Fantastic. Colored. Done. At each point, so this is one point, this is another point, this is another point, this is another point. At each point, you cut and paste this circle. So how do you paste it? So the same circle, I'll put it. Then the same circle, I'll put it. Same circle, I'll put it. And now, once I do that for every such point, I'll get a set. And that set is the Minkowski sum of these two sets. Now somebody might ask, why did you take the circle and paste it on the triangle? Why did you paste the triangle on the circle? That's actually a good question, and it turns out it doesn't make a difference. So this is the Minkowski sum. And along with the Minkowski sum, you can also scale these guys. So there is an analogous scale. So you can also scale Minkowski set. So how can you do that? If you are given, let's say, some omega subset of RD, and you are given a positive scalar or a non-negative scalar in R, then you can scale. So you multiply each element by scalar. So C omega is equal to CW for W. So if you think of a ball, half this ball is literally the ball star. Something like that, right? So if this is B, then this is half B. Now here is a good question. It's not, here is a good question and the answer is no. If you have, then is A plus A equal to 2? Is A plus A equal to 2? Where this is the Minkowski sum and this is the scaling. Turns out the answer is no. So no, this is not 2. So please don't get confused. You can't subsume adding the same guys under one bracket. But it works for balls. The interesting thing is this works for balls, but it doesn't work for too many other sets. So this Minkowski sum and this scaling are important because they preserve convex sets, as we find out. We will see I need to define difference for main variance. Oh yeah, right. So somebody was asking about this rigorous definition of polyhedron, right? Right. I'll be defining. So given any bunch of convex sets, you want to try, given any bunch of points, you perhaps want to try and find a convex set that captures all of them. So let's say there are points, there's a point here, there's a point there, there's a point there, there's a point there, point here. And now you want to find the smallest convex set that contains all of them. In that case, that would be this one. And for example, if there was this, and this, then the smallest convex set would be this guy. Avoiding this point, right? So the smallest convex set containing a bunch of points or a particular set is called its convex type. And that's what we will define. So, definition: con of A is the smallest convex set containing A, but it turns out that it's better to define it like this. Summation over I equal to 1 to n of lambda I times AI, where lambda i's are non-negative, the sum is 1 and the ai's belong to 2. So you take all possible convex combinations of of these ai's, and what you get out of that is the convex hull. So the convex hull is also the smallest set and also the smallest convex set containing it. The smallest convex set containing A. Okay? So once you have this definition and once you have these guys, we can now finally try and state some obvious results. So,
why does sum should equal to 1 by? Why that condition is necessary?
it's necessary for the following reason. What is a convex combination of these three points? So let's say I take 1 point here, 1 point here, and another point here. These guys are forming a triangle, right? What is 1 by 3 of this point plus 1 by 3 of this point plus 1 by 3 of this point? It will be somewhere here. What is 1 by 4 of this point plus 1 by 2 of this point plus 1 by 4 of this point? It will be somewhere here, closer to this guy, right? So when I take these combinations and ensure that they add to 1, what will happen is I end up getting everything that's kind of in between them. And that's the point. You end up getting everything in between them. So this condition ensures that you get everything in between all these points, right? And what happens if, for example, summation lambda I goes below 1 or above 1, then you end up getting skews, you end up getting points here and there which you don't want. So that's the reason why that particular condition is. That's the reason why. Right? So the smallest convex set containing A also ends up having this particular form. So you can write every element in that smallest set in this form. And it turns out more is true by a factor. But we are ending with not. Right. So let's write down an obvious result. Now this comes under invariance. So one thing I didn't tell you about affines, but I will tell you about convex sets, is that if I take an affine set and I flip it around, or I rotate it, or I push it up and pull it down, or if I stretch it, or if I add two convex sets, affine sets together, I still get another affine set. So there is a lot of invariance under transformations of the affine set. And the point is that the convex set also carries forward elements. Convex sets are invariant under scaling. They are invariant under rotations, translations, right? The obvious stuff. And the second, and perhaps more interesting one, is that they are invariant under Minkowski action. And the third, which I haven't talked about yet, but I need to introduce in time, is that they are in fact also invariant under closure. So if you close a convex set by adding boundary to it, you will still get convex set. And this guy, I'm going to leave some of these proofs because of time issues. So this one I leave and this one I leave. This one is obvious and this one is a good exercise for anyone starting out in the quantity. What we'll do is we'll prove the Minkowski addition one, because it's, I mean, even that is fairly obvious, but I still want to do it because it's important to just see one proof. So let's see a proof. So this is the theorem of lines. Proof of lines. So as I said, we will do only the Minkowski addition. So how do you prove that? So let's say you have two sets, omega 1 and omega 2 is a convex, right? Omega 1, omega 2 are convex. And you want to show that omega 1 plus omega 2 is convex. Right? Sorry, my handwriting got it. And you want to show that omega 1 plus omega 2 is also convex. How do you do that? You take any 2 points in omega 1 plus omega 2. So let x, let's say, and y be 2 points in omega 1 plus omega 2. Okay? Now what happens is, because they are in omega 1 plus omega 2, by definition of the Minkowski sum, this guy is the sum of elements from omega 1 and omega 2. Same with this guy. So I'm calling him that. He's going to call him that. Anyway, x is x1 plus x2 and y is y1 plus y2, where the x1 and y1 belong in omega 1 and x2 and y2 belong in omega 2. Right? Now the question is, how do we continue to proceed by definition? I mean, it's pretty much a proof by definition, so let's just finish it. Right? Now let lambda in 0, 1, oh wait, we are using t. Let t in 0, 1 be arbitrary. Then we want to show that tx plus 1 minus ty belongs in this set, right? So let's first write down what it is. Tx plus 1 minus ty, that's just t x1 plus y1, x1 plus x2 plus 1 minus t y1 plus y2. And this is just break the sum up and recombine it. Tx1 plus 1 minus ty1, tx2 plus 1 minus ty1, tx1 plus 1 minus ty1 plus tx2 plus 1 minus ty1. Now, because omega 1 is convex, this guy here belongs in omega 1. And because omega 2 is convex, this guy belongs in omega 1. Consequently, this guy belongs in omega 1. Okay. So very easy proof, as you can see. And to be fair, the rest are quite easy. This is just a limit argument, and these things are just a case of, if you have x and y, there's a line segment between them. If you scale, that line segment just gets scaled. If you rotate, the line segment gets rotated. If you translate, the line segment gets translated. So literally nothing changes from a geometric point of view. So now we've seen that convex sets are extremely useful objects. Right? We've seen that they're invariant under a lot of scaling. So they're extremely flexible objects. They're likely to appear a lot in real life. Now what we will see is that convex sets have an analog of the nearest neighbor property. This is a theorem. Just want to look at the guys next. Some Russian guy wrote this up for the first time. Then I haven't been able to find his paper. The paper is in Russian, so the problem is it was difficult to retrieve it. But of course, now it's been written up in some Polygons theorem or something like that. But anyway, all that's important is that later on it was written for Hilbert spaces and for Hilbert spaces without this. So, here's a theorem which we call as the nearest neighbor property. Oh wait, before that, I just 2 minutes to make sure that these small things are sealed up. So I just define what open, closed, compact and bounded are. So definition: a set omega subset of Rn is 1 open if for all x in omega you can find a radius Rx such that the ball of radius x Rx is contained in omega. Okay? 2, it's called closed if omega complement is open. 3, it's called bounded if there is a constant, some large m greater than 0, such that the norm of x is less than or equal to m for all x in omega. So basically speaking, it shouldn't grow too large, it should stop at some time. And 4 is compact. People will know that this is not a proper definition of compact, but for Rn it doesn't matter. If it is closed and bounded. So just to be sure, there is another containing its limit points, which is far more easy to understand. So if you're thinking of closed, don't think of omega complement. Just think of a set which contains its boundary. For example, if you have an open ball, so an open ball doesn't contain its boundary. Its boundary won't be contained in it. But I can close it. I can sort of include its boundary in it, and now all the so-called boundary points are part of the set itself. So that set becomes closed in that sense. You can't get out of the set by sequences, right? So the way to think of closed perhaps is via the limit point. So contains its limit points or contains its boundary. Maybe even that's better. It just contains its boundary, right? Think of it geometrically that way. Once you do that, you can then appreciate the nearest neighborhood. This is very interesting because in Rn there is a converse to this result that basically will state that the nearest neighbor property is true only for closed and convex sets. So let omega, let's say for Rn, be closed and what is it like closed? Sorry, closed and convex. Then the following is true. For all x not in omega, there is a unique in capital letters y in omega such that the distance from x to y is less than the distance from x to y prime for all y prime not equal to y belonging to A. So if I take any other point in omega, that will be strictly further away from x than y. So y is a unique guy that is the nearest neighbor to x. So for example, this need not be true if x is not convex. For example, let's say x is this set, kidney bean or something like that. If I take a point here, it's obvious that both this guy and this guy are the nearest points. So these guys will be equal, they have equal distances. But then that obviously means that it isn't a unique. Because there's this point, they're both distinct, but they're both nearest neighbors in this set, right? So convexity is important. Actually, it turns out that convexity is important for uniqueness. Uniqueness is where convexity is used. Closure is used only for existence. There is. Therefore, the is part will require unique. So if I stop at there is a y in omega, if I remove this word unique, then I don't need the word convex. I can use the word closed. But I need the word convex for uniqueness. Okay, let's start. The proof is going to involve parallelogram. And you're going to see the Euclidean norm in its full glory. Right. So we're going to use some basic machinery here, some Cauchy sequences around here and there will be thrown in. And then at the end we'll throw in a couple of Pythagoras theorem and parallelogram problems. Okay, so it will be very quite standardish with a dash of first year analysis. So it's a very nice proof, right? Let me show you first how to prove it. How do I prove it? Visually. Okay, visually. Let's say this is a convex set. Closed convex set. Okay? Okay, to say a command. That. And drawings are horrible. So this is x, right? Now, what I do is, this quantity vxy prime, I can continue to try and minimize it, right? In the sense that there is a minimum distance from x to this point. This is some non-negative distance. And when this is not non-negative, this is literally a positive distance. So therefore, you can find points that kind of come closer and closer to that. So you can find like a sequence x1, x2, x3 and so on, which is coming closer and closer to x. So x1, x2, x3, these distances are reducing. So the question is, how can I create a point, a minimum point out of that? The answer is that this will form a Cauchy sequence using the parallelogram law, and then I will show that it converges because it's a closed set, because it's a limit point, and therefore you can show that it will be contained within this set. Then for uniqueness, I will use a smart Pythagoras. And uniqueness is where convexity is like seen in its full glory in some. Like मात्रा दिक्कत ऐसा हो गया हमारा, right? So that was usually the proof. So first we start by quantifying that distance. Let's give that distance something. So let r be the smallest distance from a point to another. Okay, let me first say claim r greater than 0. Can somebody quickly tell me why r greater than 0?
Because it's not in the center.
Exactly. See, if r equals to 0, then x will be a limit point. If r equals to 0, then you can keep finding points which are closer and closer to x, and x will become a limit point. But then we already know that the set is closed, so it contains all its limit points, and have deliberately assumed that x is not in omega. I have deliberately assumed that x is not in omega, right? So, because of that reason, r is greater than 0. Although I am not using this fact, this is still important. Now what we do is, we know that r is the infimum of the set. So what do we know from the property of the infimum? It means that something just greater than r cannot be the infimum, right? Something just greater than r is not the infimum. So let n, okay, let's use a different thing. We are using n for the, no rn, so let's use n. Let m greater than equal to 1 by the infimum property r plus 1 by n is not an infimum, right? For all n. So what does that mean? What does it mean if it's not an infimum? That means that there are points whose distances are strictly smaller than r plus 1 by n. So there exists xn in omega such that d of x comma xn is less than equal to r plus 1 by n by the infimum property. Now we are going to claim is that the xi form a Cauchy series. So the claim is that the xi are Cauchy series. And now we are going to prove this. The proof is going to involve the parallelogram law. Actually, this proof is it's very tailored to first years, in the sense that there is a proof that is far more high level and easy to work with. If you are at a high level, you won't require Cauchy sequences and so on. But this proof is just so beautiful. So let's do this, right? Let's take two of those points, xi and xj. Okay? So now I'm going to draw a diagram. This is xi. This is xj. This is 0, and this is the point xi plus xj, right? And this forms a parallelogram, right? This forms a parallelogram. So this is a parallelogram, and opposite sides are equal, right? What do we know from the parallelogram law? We know from the parallelogram law the following. So the parallelogram law implies that d of xi xj the whole square, which is one of the diagonals, plus the other diagonal. So d of xi plus xj comma 0 the whole square is equal to d of, is equal to d of 0 comma xi whole square. So basically speaking, you just get the norm. So here it's just write norm. Norm of xi plus xj whole square is less than equal to, sorry, not less than equal, it's equal to 2 times norm of xi square plus norm of xj square, right? This is what the parallelogram inequality tells us. Now what I am going to do is, I am going to transfer this norm xi plus xj whole square to this side, and I am going to place an inequality that will tell you that this guy is small, and just see how that happens, right? How will that happen? That will happen as follows. So d of xi xj squared is less than equal to, no, not equal to 2 times let me just take a look at that. I'm sorry for that. Okay. So yes, that's right. So equal to 2 times norm xi square plus norm xj square minus norm of xi plus xj the whole square. Right? This is how it works. Now, what are the inequalities that are in play here? What are the inequalities that are in play here? Let's take this. Am I assuming without also deliberately? Okay. This is in x. This is in 0. I'm so sorry. I'm terribly sorry about it. This is in 0. This parallelogram shouldn't be created out of 0. It should be created out of x. But I'm taking the distances from x. xj. And this is some point here, right? Some point here on the end of the x. Some v or something. The important, yeah, right. So this is some v or something. I'm terribly sorry about this. Now if you do the parallelogram law, then you will get what you need. So now if you do the parallelogram law, you get d of xi xj the whole square plus d of v comma x the whole square. This is equal to 2 times d of xj comma x whole square plus d of xi comma x whole square. Now things are beginning to happen. Right now what's happening is that this implies d of xi comma xj the whole square is less than equal to, well I'll put the less than equal to, first keep it as equal to, okay, is less than equal to this guy plus this guy minus this guy. So 2 times d of xi comma x the whole square plus d of xj comma x the whole square minus d of v comma x the whole square. Okay? Now I'm gonna substitute these values, right? Less than equal to, now d of xi comma x is less than equal to r plus 1 by n, right? So 2 times r plus 1 by n the whole square. The other guy, well, okay, no, I'm sorry, I'm using ing. So let's say I square plus 2 plus 1 by j square. And now, okay, let me just, I'm going to write something and I'm going to ask you guys why this is. I claim that d of v comma x is at least 2r. I claim that d of v comma x is at least 2r. If somebody doesn't figure out, I'll tell it. So the claim is that this distance that you see here is actually greater than 2r. Exactly.
That means xi and xj are at least r distance apart.
So these are at least r distance apart. So therefore this guy will at least be 2r distance apart. That's how that works. Right? It will work according to the parallelogram triangle inequality. So d of v comma x is at least 2r, and these guys are at least r plus 1 by I and r plus 1 by j. So with this inequality now, can somebody, now you can just do your algebras and simplify this inequality, and what will you get once you go to the other end? once you simplify all that algebra, you just get d of xi xj is less than equal to r times 4, right? Is there a 4? 4. Yes, that's it. So r times 4 by I plus 4 by j plus some 1 by I square plus 1 by j square or something like that. You will get something like this. And now if ij go to infinity, sorry?
That xi is 0 to square.
Sorry. So sorry. Right. Exactly. Absolutely. So dxi xj squared is between these guys. If I and j go to infinity, then this guy goes to 0. This guy goes to 0 using usual epsilon delta arguments. But then at the same time, dxi xj is also a positive point, also a non-negative point. So by squeeze theorem, d of xi xj goes to 0. i.e. it's a Cauchy sequence. So far we have not even used convexity. We have only used a parallelogram, but we have used any sort of convexity. Now that means that xi is a Cauchy sequence in omega. So xi in omega, Cauchy. Omega is closed. So that means there is a point x such that xi converges to x and x is in omega. Now what is the speciality of the distance function which I wrote to you? If you recall the formula for the distance function, it's only given by some square roots and summations and so on. So it's a continuous function. And because it's a continuous function, what exactly continuity means? Well, okay, let's not put x already there, x star. What will happen is that d of x comma xi will go to d of x comma x star as I goes to by continuity of distance. And therefore d of x comma x star is equal to r. Because this particular sequence that you see here is being squeezed by r plus 1 by n on one side and by r on the other side, because r is the infinite. So this guy is equal to r. And therefore x star is the required candidate. So x star has been found. Right? Now that x star has been found, we need to go and take a look at uniqueness. How does uniqueness work? Uniqueness works on the following fact. So uniqueness. Uniqueness works on something very simple. Suppose that, let's say this is x and this is omega, and this is a point x1 and this is a point x2, okay? And x1 and x2 are apparently the closest points to x, okay? Now let's throw out omega. Okay, so now these line segments are there and they are the same length because they are both of length r. So both of these are of length r. So, supporting and separating hyperplanes theorems are two very fundamental theorems in the study of convex forms. The recording on again. Okay. So, what do we mean by separation? You see, when we think of data and we want to cluster data, we want to typically, by clustering, we talk about separating data, right? For example, these are the marks of D1, these are the marks of D2. Now, if I scatter if I take the marks of D1 and D2 and mix them together, then the art of clustering is to kind of separate them after that, right? So, separation is a very natural thing to ask for sets. So what do I mean mathematically by separation? I mean the following. For example, let's say you have a set like this. This kidney bean is my favorite. Always there for non-fun. If I have another kidney bean like this, how do I separate these sets? I need to kind of separate them by drawing this kind of weird jiggly line. Right? So this is some kind of separating line. Not separating line, it's some kind of curve. Right? Now, if you look at convex sets, it's much easier to separate. If I have convex set here, then if I have convex set here, I can literally draw a line between them. I can literally always draw a line between them. And in 2 dimensions it's a line. In n dimensions it will be a hyperplane. It will be an n minus 1 dimension hyperplane. And that's the idea behind the separating hyperplane. So what does the separating hyperplane theorem says? It says that if you have two convex sets which are disjoint, you can separate them using hyperplane. And I won't be proving this. It kind of is it isn't exactly a corollary, but it's nearest neighbor plus 5-6 lines of code. So here, separating one. There's another one called supporting, which I'll just give you an idea of how this works. I won't explain this. So given omega 1, omega 2, subset of Rn, disjoint. Disjoint.
Is it like expanding at polarizes
No, please don't confuse the polarized surfaces. There is one naturally occurring example of convex sets. They have nothing beyond that. They have uses and optimizations. For something as fundamental as this, you require nothing more than clear analysis. Disjoint. There exists a hyperplane. Not a unique one, by the way. So, for example, if there is a convex set here and a convex set here, this guy will separate, this guy will separate, this guy will separate. So, there is no way to expect unique. But for sure, you should be able to expect at least one hyperplane. There exists a hyperplane H such that if H1 and H2 are the half spaces associated to H are the half spaces associated to H, then one of them will be contained in H1. So let's say omega 1 is contained in H1. Omega 2 is contained in H2. And that's the point. You have a hyperplane system. On one side, omega 1 is there, on one side, omega 2. So it's helping separate these two things, right? And I'm not going to talk about the proof of this. What I will talk about the proof of is what is called as a supporting hyperplane. Let me give you an idea of what a supporting hyperplane is. Well, a supporting hyperplane at a point on the boundary is basically a hyperplane that touches that point and kind of keeps the convex set on one side of it. So for example, let's say this is a convex set, okay? And I want to draw a separating hyperplane at this point. What is that? That will be like a hyperplane which just touches this point and runs away. So it's like this. It's like a tangent. Exactly. It's like a tangent. But it's not necessary that it doesn't touch any other point. For example, if I have a square and I'm trying to draw the separating hyperplane here, that separating hyperplane could be this one. It could be this one. So it's any hyperplane such that it touches this point, but the entire convex set is on one side. And that's the point. So let x in omega, but it needs to be on the boundary. So what does it mean for it to be on the boundary? X is a limit point of omega complement. This is what it means for it to be on the boundary, right? When something is on the boundary, you can approach it from outside. So So that's what it means to be a limit point of omega complement. So typically the boundary, so any point which is an omega but a limit point of omega complement is called a boundary point.
One has to be open and one has to be closed.
Sorry?
If one convex set has to be open and closed.
No, not really. Nothing like that. No, absolutely no condition between the complement. So let x be omega, where x is the limit point of omega complement. Then there is one that as I mentioned, there is no need for uniqueness. Look at this square. There is no need for uniqueness. There is a hyperplane H, hyperplane, such that if H1 and H2 are the half spaces associated to H, which I won't write and really direct, then omega is contained entirely in H1 and x is in H. So this point x should be in the hyperplane and omega should lie on entirely one of the half spaces. And this is the supporting hyperplane. Now how do you prove the supporting hyperplane theorem, right? Well, I mean, you are basically asking the question of how do I take a tangent at a point in some sense. But you are working with more abstract tools. You don't have stuff like, oh, this is a differentiable smooth surface, I'm going to take the derivative and I'm going to fly around and whatnot, right? You can't do that. So if you can't fly around, it's okay, you can run. And it's enough to run even if you have convex actually. So, what is a sketch of this tool? Sketch. Only by 345 data. Sketch. Right? Let's draw a large convex surface. For this I needed one huge part of my graph. So I'm going to take an equal huge part of it. Okay, jump on. Okay. So this is my convex set. Does it look convex? Okay. Ah, yeah. Convex set. Right. Okay. Let's take the point now. Now I get all my colors. Okay, so this is your point. Okay, let's see. This is your point, which we will call as P. Okay? What we are going to do now is we will consider points from the outside approaching P1, P2, P3. It doesn't look like they are approaching. I mean, it looks like they are approaching, but I am drawing them far away for your convenience. Okay? So the PI's are a bunch of points that are approaching P from outside. From outside. Okay? And what's happening is, what we will do for each of these PI's is that we find a point here, the unique point here, that's closest to P. So for example, for P1, let's take some x1. Okay? For P2, okay, sorry, this is the interior. So we stupid for x1. And P1, so the distance between P1 and x1 is the smallest distance between P1 and any other point. So literally P1 x1 is like the smallest distance in some sense. And then for P2 you find its nearest neighbor, P2 x2. Right? And now you take P3 x3. Right? And now what's happening, if you notice, is that there are directions associated to these lines. So when you go from P1 to x1, you are traveling in a certain direction. All that vector is V1. Unit vector is V1. So V1 is a unit direction in which you are traveling from P1 to x1. Then you travel from P2 to x2. So that's another unit direction, V2. Then from P3 to x3. So that's another unit direction, V2. So Pi converges to P. Xi is the nearest neighbor of Pi in omega, and Vi is the direction from Pi to Xi, unit direction. So I am not writing unit, but whatever, I have written the hat, so that should be good. Right? As this converges, do the Vi's converge? As Pi converges to P, do the Vi hat converge? Is a question worth asking. And what if it does converge? If it does converge, then it will converge to what is effectively speaking a tangent sort of situation. It will feel like it's kind of tangent to the surface, right? And if at that point you take the hypersurface that is parallel to that is normal to that. So you take everything here that's perpendicular to this particular direction, like that, then that's your hyperplane. And that is how you get your supporting hyperplane. So do the VI converge? Yes. And this limit direction V, which is the limit of the VI hat, that determines the supporting hyperplane. And that's a sketch of the proof. So the point is, we've used the nearest neighbor property here. We approached this point from the outside, we found these directions, we do some jugglery and make sure they converge, and wherever they converge, that is a particular unit vector, get everything that's orthogonal to that. And make sure that it passes through this point, and enjoy, make the charge. Right. So that's your supporting hyperplane theorem. So the interesting thing about supporting hyperplane theorem is that just like how we saw that the nearest neighbor property is equivalent to having a closed is equivalent to having a closed and convex set. Actually, it turns out that even supporting hyperplanes admit some kind of theorem. So another interesting fact along with this guy is that nearest neighbor in Rn is equivalent to being closed and convex, and existence of supporting hyperplane at every boundary point is equivalent to being convex. Wait, convex if a set is closed. So if omega is closed, then if omega is closed, then if it has a supporting hyperplane at every point, it is convex. If it is convex, it has supporting hyperplane. You need to assume this closure condition. That's just a technique. No, this is only for Rn and only for Euclidean distance also. May I say that? So if you cut out Euclidean distance and you start taking random distances, the magic of convexity vanishes. That's very unfortunate, but it's true. So this is another interesting result. So now we found three ways of thinking of convex sets. We found the nearest neighbor property and we found the supporting hyperplane property. Now here is an interesting result. Not interesting, it's just pretty much a corollary of the supporting hyperplane theorem. You see, if I want to understand a convex set, this guy says that it's enough to understand the supporting hyperplanes on each side. Because it's like, if I'm trying to form the convex set, I'll first press it from the bottom, then I'll press it from the side, I'll press it from here, and I'll slowly form it, right? As if some potter, making a clay pot or something like that. So these supporting hyperplanes are kind of like people pressing at that point with that angle and forming the convex set. So every convex set is kind of determined by its supporting hyperplanes. So this is very important, what I'm saying right now, because convex duality, I don't think anybody can live without convex duality. So the idea behind convex duality is that every convex set is determined by its height. Where I'm using the word determined a bit loosely. Here, what's his name? Every convex set closed is determined. So I'm not taking it rigorous by itself, by its supporting. And you can kind of get the idea, right? The compression idea is precisely what it is. But already around 350. How long can I put? You people are enjoying, no? really honestly thank you so much. Wow, I can't believe it. No, so at this point we are now going to fly into Krasnoselski's theorem. So what I am doing is, again for the interest of time, I am going to I'll present like some standard results. These are results that you would learn if you did a first course in convex geometry, but that's not offered here, and that shocks me. So that really shocks me. So it's like, because it's something that anybody who wants to do applied mathematics today has to do convex geometry. I mean, not convex geometry, but convex optimization. So it's ridiculous that it isn't there in the syllabus. I feel like hitting my hands. I mean, not sometimes, all the time. Anyways. Now what I am doing is I am coming to some kind of more regularity that's associated with convex sets. I'll quickly explain what I mean. Yeah. Let's start with the following theorem of Radon. Nothing to do with the Radon-Newton theorem anyway. No, absolutely nothing. Okay, before that, a small typo. In a sense that we are now approaching a subsection called Krasnoselskii. So we are now approaching Krasnoselskii. That is all the pronunciation. Not rushing, but now you know what's important to distinguish. Krasnoselskii. Okay, let me say it for everybody then. Krasnoselskii. Okay. Krasnoselski's theorem. We are going to approach this. So I'm not going to state this right now. I'll first state the theorem right now. So what does Radon's theorem say? Radon's theorem. Okay, fine. Before I'm going to approach Radon's theorem, let me talk to you about something terribly obvious, right? I'm able to see you up. I'm able to see you. I'm able to see you. But the minute I put this bottle in front of myself, I'm suddenly not able to see someone in the crowd over there, right? So the reason why I'm visible to all of you and you all to me is because I'm standing in a position where the line segment between me and you is uninterrupted, right? So there is an idea of visibility that you can associate to convexity in the sense that, so you think, let's imagine that you're a watchman at an art gallery or something like that. If there's a room like this, okay, and there's a painting here, P1, and there's a painting P2, a watchman that's over here will be able to watch over both these paintings and make sure that any thief will not be able to steal them. But if a watchman stands over here, he's obviously not going to be able to see what happens in P1 because his line of view is obstructed. And the idea behind Krasnoselski's theorem is that, I mean, it's actually called the Krasnoselskii art gallery theorem, is that in some sense we can provide sufficient conditions under which one watchman is enough to watch an art gallery. That's the point. So it's called Krasnoselski's art gallery. And there are more. So the interesting thing about the art gallery theorem is that recently people have been proving extensions of the art gallery theorem to a quantitative sense. Even as recently as 2018, 2019, there are results. Like Klee's theorem is pretty old, but there are some great huge extensions of this to some quantitative versions and so on. But on the way to Krasnoselski's theorem, the point is we see two of the most classical theorems that are associated with convex sets. One of them you won't see, which is scalar theory, but that's corollary. So what we will see first is the so-called Radon's theorem. And what does Radon's theorem say? Radon's theorem says that if you have paintings scattered around, there's one point which you can choose which will kind of watch over one bunch of guys and watch over another bunch of guys, as long as you partition the two in a certain way. So for example, what I'm trying to say is let x1, x2 up to xr be in Rn, and now I insist on r greater than equal to n plus 2. Okay, so I insist there are at least n plus 2 paintings or whatever. Then that's all I need to do. You can partition these guys. So then there exists, a partition So S1 and S2 of this set okay, such that con of S1 intersection con of S2 is a non-empty set. So basically speaking, anything in the conv of S1 can watch over everything in S1. Anything in the conv of S2 can watch over anything in S2. And the point is that every set of size at least Rn by n plus 2 can be broken into two parts such that one watchman can watch over these parts as well as one watchman can watch over that part. And that's amazing. So now we're going to prove this Redon's theorem. And Redon's theorem is proved by Minkowski. In case you didn't know. Right? We'll go till 4:30. Is that okay?
Yes.
Wow, thank you. Okay. And not a drop more than 4:30, unless when people ask questions. If it goes on to please restrict so many comments that you will read. Okay? Right. Proof. Okay. Oh, fantastic. We're going to use some linear algebra next. This is going to be good. It's nice to know that I can use things that first year understand. Okay, we're going to be using the Rationality theorem. Raja is going to be proud of me. Right. Let's start by defining a linear map. Okay? So, proof, define. So why are we defining this linear transformation? Well, you want to use a linear transformation's kernel to say to create S1 and S2. Okay? But why does it have a kernel? Why does it have a non-trivial kernel? Try to it. Let's go. Just watch a minute. Define a linear mapping from, let's call it L, from R small r to, okay, this is actually Rn plus 1, but I'm just writing it for convenience as Rn cross R. You will see why. So this is actually Rn plus 1, but I'm writing it as Rn cross R and you will see why. How is this defined? This is defined as follows. L of alpha 1, alpha 2 up to alpha r is equal to, first is the Rn component of this, which is basically summation I equal to 1 to r alpha I xi, and summation I equal to 1. No, you need a summation, pardon. Summation I equal to 1 to r alpha I. Okay, so in the first what I have done is I have created a sort of some kind of sum of the xi's using these alpha i's. These alpha i's are not convex, by the way. They are not between 0, 1 or something like that. They are just arbitrary real numbers. So just think of this as an arbitrary sum of the x's, and this is just their sum. So this is sum of the alpha i's, and this is a sum of alpha i's and x's. Okay. Now r is greater than or equal to n, which means that this dimension of r, which is just r, is greater than or equal to n plus 2. But what is the rank of n? The rank of n is at most the dimension of this guy, and this guy is n plus 1. So rank of n is less than or equal to n plus 1. So the dimension of this guy is at least n plus 2, but the rank of this guy is at most n plus 1. So that means at least there is a gap of 1. So that implies that by rank nullity theorem, let's write it for the sake of CRB Raja. By rank nullity theorem of CRB Raja, the kernel of L, the dimension of it, is greater than 0. And therefore, there are alpha i's which are non-zero, which satisfy this and we are going to use these alpha i's. Specifically speaking, we will use the positive and the negative. Okay, so alpha 1 up to alpha r be in the kernel of L where at least one alpha I is not equal to 0. Now what does that mean? That means that this sum is 0 and this sum is 0. So that means that summation I equal to 1 to r alpha I xi is equal to 0. Summation I equal to 1 to r alpha I is equal to 0. Where this is a real number 0 and this is a vector 0. Okay, so this is the element 0 in R and L, whereas this is just the real number. So I hope that's not confusing. But once that isn't confusing, what we've done is we've kind of made sure that we can adjust these xi's in such a way that they come to 0 and the coefficients themselves kind of get adjusted and come to 0. Now what we'll do is, because the alpha I sum to 0, if there's a positive guy, there has to be a negative guy to both. So the point is that you can separate the alpha i's into positive and negative guys. So separate. So let S1, so now we separate. Let S1 be the set of all i's such that alpha I is greater than or equal to 0. And let S2 be the set of all i's such that alpha I is less than 0. Okay? So now we have done this separation. And let's also do another thing. Now we don't need not really. So once we have these sets, what we are going to do is we are going to prove that if I take xi for I belonging in S1 and if I take xi for I belonging in S2, okay, I should not call S1 and S2 are a partition of the xi, right? If I call them as E1. This is just notation stuff. Everybody gets stuff. Okay. So what I will do is now to show that con of x ti in t1 intersection con of x ti in t2. You need to show that this is non-empty. So I need to find a guy that's a linear combination of both all the guys in T1 as well as all the guys in T2. Right? What I do for that is something extremely smart. I'm going to be using this equation that you see. In this equation, I'll separate out all the S1 terms on one side and I'll separate out all the S2 terms on the other side. Okay? So summation I equal to 1 to r alpha I xi equal to 0. What does this imply? This implies that breaking the sum into two parts, summation I in T1 alpha I xi plus summation I in T2 alpha I xi. Right? Right? This is okay? Now let me quickly make sure that I have this part. Perfect. Okay. Now what I do is here also here the same thing is true, right? So I write this as summation I in S1 of alpha I, not S1, T1 of alpha I. This time I take whatever is T2 to the other side, so minus summation I in T2 alpha, right? Because they kind of balance each other out. Their sum is equal. Let's call this quantity as alpha. What's capital A? Okay, let's call it as beta. Okay, once we call this quantity as beta, what we can do is we can create particular linear combinations here that will turn out to work. So let x is going to be a point that is actually going to sit in both these convexes. And let me quickly explain to you how that's going to work. Summation I in S1 of alpha I by fancy beta, fancy beta, not beta. So this x, write it as summation I in Si, alpha I by beta times xi. And now this guy is in the convex hull of S1. This is in the convex hull of S1 because I have written it purposely as a convex combination of the x1. And the point is, beta is written in such a way that I in
Yeah, that should be.
T1, yeah.
T1.
It's just, so basically, SI is just SI is xi for I in T1, and S2 is just xi for I in T2. That's not a big deal. That's not a big deal. That I will do. So x can be written as a convex combination of elements in S1, and similarly, x can be written also as a convex combination of elements in S2. Because literally, if you look at just do the minuses and so on, you will literally see that it's also summation I in T2 of minus alpha I by beta times.
Can you repeat the last part? What is it? Why is it S1? Why it belongs to S1?
Okay, I can do this. Before that, I will define S1. So just so that everybody knows. Okay, so S1 is equal to xi where I is in T1, and S2 is equal to xi where I is in T2. Okay. What I have deliberately done is I have created an element that is a convex combination of all the i's in T1. Deliberately created it, and because I have created it in this way, and because the summations of all the alpha i's are equal to beta according to this equation, this is a convex combination of some bunch of elements belonging to S1, and therefore it belongs in the convex hull of S1. But at the same time, because of this relationship, and because again I can divide by beta, I just get this equality. This follows from here and from here if you combine both of them. So x is also equal to this. X is equal to this, and x is equal to this. And this, on the other hand, is a convex combination of the guys in. So I have now created a watchman that can watch over both S1 and S2. I have literally explicitly created it. It's there for you to see. The only thing that isn't explicit is Raja's nullity theorem, nothing else. Okay? For which you have to take CRE Raja's and not me. Right. So Radon's theorem is done. Now Radon's theorem generalizes to a fantastic result known as Ellis theorem. And Ellis theorem is interesting because that still has research which carries which has a lot of use in optimization nowadays. So what is they are doing is they are converting these results into qualitative estimates. You see, in mathematics there are two kinds of estimates: qualitative and quantitative. Qualitative means there is this object, there is this object. Quantitative means there are these many objects, there are at least these many objects. So what's happening now in research is that quantitative estimates are turning into qualitative estimates. For example, you might ask the following question. You might be like, what conditions can I put so that this guy has a large size? How can I make more than one watchman fit in here, for example? How can I make sure that no watchman perhaps fits in here? Something like that. So how many guys are in this set is a matter of research. And that's basically what happens nowadays. That's converting all these qualitative results into quantitative forms. Right? Where in Ellis. This Ellis theorem is fantastic. What it says is that, okay, what it says is the following, right? If you have some bunch of convex sets scattered around, say you have some bunch of convex sets scattered around, okay? In RD, these convex sets are scattered around. If any d plus one of them intersect at one point, at least one point, so let's take any d plus one of them, maybe this guy, that guy, this guy, and you take any d plus one of them, and somehow it happens that they intersect somewhere. So there's one place where all of them, not one place, but probably more than one place where they all intersect. Maybe they all intersect here or something like that. And this happens for every plus one collection. Then it turns out, according to Ellis theorem, that they all, literally all of them together, intersect in at least some point of time. So Ellis theorem is basically a ridiculous result. It says that if something something happens at a finite level or between some bunch of collections of sets, it literally happens for all the sets together. And what does it say? Number of sets may be arbitrary, uncountable. In fact, we require uncountable Krasnoselskii. But so I'm going to state a version of Ellis Theorem that's easy to prove. There's a harder version which I'll just abstract on, okay? Which is not very hard, it just requires compact size. Let C1 up to CR be convex sets. Do I need to? No, for this normal I don't need. So I have finitely many sets, but this time I have R greater than or equal to n plus 1. So all these sets are sitting in Rn. But with R greater than or equal to n plus 1, if for all, say Ci1, Ci2 up to Cin plus 1, choice of convex subsets, it is true that intersection I equal to 1 to n plus 1 j equal to 1 to n plus 1 of Cij is non-empty, then intersection I equal to 1 to R of Cij is also non-empty. So what I am saying is, if something holds for any choice of n plus 1 sets, it literally holds for all of them. So there's one guy, if for each n plus 1 guys, there is one guy who is able to watch all of them, then there is literally one guy who is able to watch literally all of them. All of them.
The last intersection should be just over Ci, right?
Sorry, correct. Ci, not equal. Okay? This is another result that's going to get proved by induction. Did I prove the previous guy by induction? Oh, sorry, I didn't use induction. I'm sorry. Radon didn't use induction. Radon used linear algebra. Right? So Ellis Theorem will use induction. This proof will be by Radon. And what's the idea? The idea is the following. You will kind of, if you're using induction, you need to reduce. So what you do to reduce, you kind of remove one set out at a time. You generate points, and then you use Radon's theorem on it. Proof by induction. For R equal to n plus 1, it's obvious. Because that's literally the hypothesis, right? If R is equal to n plus 1, then you literally take all of them. That's a valid collection. And by assumption, for that the intersection is non-empty. So you're done. So for n equal to 1, obviously. For n equal to 1 of this.
R equal to n plus 1.
R equal to n plus 1.
Okay.
So we'll induct on R minus n.
You can't, I mean, same thing. Okay, so now, true, if you assume it's true for R n minus 1. Okay, so not R n minus 1. You assume it's true for R minus 1, and we'll show that it's true for R. We'll show it's true for R. Okay? What's going to happen here? If we've already shown that it's n plus 1, right? We've already shown n plus 1. Now, if you're dealing with the induction case, R is at least n plus 2. So, Radon's theorem is available to us. Radon's theorem is available to us, right? So, that means I.e. Radon's theorem is available. Radon's theorem is everybody able to recall Radon's theorem? Is it still on the board?
I think it's fine.
Does anybody need help recalling Radon's theorem before we do this? Okay, please consult your notes, okay? Otherwise, please let me know and I'll rewrite Radon's theorem. Right. So, Radon's theorem is available. What we'll do now is the following. So, let's say those sets are given C1 up to CR. Okay? What we'll do is, we'll take one guy out of this collection and apply induction. Take one guy out of this collection, apply induction. So, for each for each 1 less than equal to I less than equal to R, apply induction case on just give me a minute. Of course. Okay, I'm right. I'm just do one computation. So for 1 less than equal to I less than equal to R, you apply the induction case on everything except I. So you apply it on C1, C2 up to Ci minus 1, skip I, Ci plus 1, Ci plus 2 and up to Ci. Okay? So you apply induction case to these ones. What does the induction case tell you? The induction case tells you that there is a point xi that will belong in the intersection of these values. So all except I that will belong in the intersection of C1, intersection C2, intersection up to Ci minus 1, intersection Ci plus 1 because I skipped, intersection dot dot dot, intersection Ci. How many intersections did I say there? Anyway, so there are these points, and how many of these points are there? R of them. And R is at least n minus 2, n plus 2, because we've already dealt with n plus 1. So, apply Radon's theorem to this collection. Xi 1 less than equal to I less than equal to. See how beautiful this is. Induction case, removed 1. That's so obvious. I got points, I just told you Radon's theorem, apply Radon's theorem. Like some Sidhu, I can raise my hand and do it. Okay. So once you apply Radon's theorem, what do you get? You will get these two subsets, right? So now what I do is, for convenience, I think I have to denumber these subsets. I not denumber without loss of generality and assume some structure. It is for notational convenience. Okay, right. So there exists S1 and S2, which is a partition of this set x1 up to xr, such that conv of S1 intersection conv of S2 is non-empty. Okay? Let's take a point in this intersection. Let x star, I'm going to rename this because I have x stars, in conv of S1. Now what happens when something is in the intersection of conv of S1 and conv of S2? We are going to show that x star actually ends up belonging to each of these sets. And let me quickly explain to you why. For convenience, so here at this point I could do some kind of notational jugglery, but I just want to avoid that. So let's just assume that it so happened that S1 was x1, x2 up to some xk minus 1, sorry, xk, and that S2 was xk plus 1 up to xr. This need not be true, right? It need not be true that this was the exact partition, but for notational convenience, let's just assume that it was the case. You can renumber the points xi and so on and things or that is the case. So when mathematicians do this, they write what is called as a without loss of generality. So I'm going to do that as well because I am a mathematician. I am a mathematician, mathematicians write WLOG, so I write WLOG. Right? So without loss of generality. This is something that kids love, okay? Whenever, they have to make some kind of logical jumps, which are actually not logical jumps, they'll make it and they'll be like, without loss of generality, right? And then they will end up making too easy, they end up making life wrong. Right? to are like this. Now what we are going to show, what do we need to show? To show that this point x star that has been chosen so specially, it actually belongs in all of these CIs, because that's what we want, right? By Ellis theorem, we want a point that's literally in all of the CIs. So we want to show that it's in all the CIs. To show that x star is in CI for all 1 less than equal to I less than equal to R. Now see what happens. This is beautiful. Okay, x star is in con of S1, yes, but I'll just write down x1, x1, x2 up to x. Okay. So x star is in the convex combination of these sets, right? But now look what's happening. This is beautiful. Where is x1? x1 is in C2 intersection C3 intersection dot dot all the way, right? x2 is in C1 intersection C3 intersection dot dot. x3 will be in C1 intersection C2 intersection C4 intersection dot dot. But the point is, all these sets, all these points that you see here, x1, x2, x3 up till xk, they all belong in ck plus 1 intersection ck plus 2 intersection dot 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 intersection cr. So each xi for 1 less than equal to I less than equal to k belongs in ck plus 1 intersection ck plus 2 intersection dot 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 intersection cr. Is this clear? If this is not clear, please stop me. Is this clear? Yeah. Okay, take any of it. I thought people would be more stuck on this. I was stuck on this for like some 20 minutes. Anyway, so x star is in the con of these guys, and each of these xi's belongs in this set, and this set is convex because convex sets are closed under intersection. Convex sets are closed under intersection. Why are convex sets closed under intersection? Because that line segment isn't going anywhere. If you have a convex set like this or something like that, and there are points, there's a point x in the intersection and there's a point y in the intersection, then the line segment lies in one of them, it lies in another one, it lies in the third one, so it lies in all of them. And therefore, convex sets are closed under intersection. This is a convex set. This is a convex set. But what is the definition of con? Con, by definition, is the smallest convex subset containing each of these points. So, con of x1, x2 up to xk is the smallest convex set containing x1, x2 up to xr, right? Up to xk. But this is another convex set that contains all of them. This is a convex set that contains each of these x's. But the smallest one is the con. So therefore, the con of these points must be a subset of this. And because this guy is in the convex, x star must be this. Let me do this. Let the duster and lock the duster. Okay, I'll run this. So, because this is the smallest convex set contained in these guys, con of x1, x2 up to xk is actually a subset of ck plus 1 intersection ck plus 2 intersection dot 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 intersection cr, and x star belongs in this. So x star belongs to this guy, belongs to this guy, belongs to ck plus 3 all the way up to c. So implies that x star is in ck plus 1, is in ck plus 2, is in up to is in cr. So x star. x star belongs in all sets k plus 1 onwards. Now we need to show that x star belongs in all sets k plus 1 before k. But how do we do that? Well, the answer is obvious. We only use the fact that it belongs in S1 so far. So, similarly, x star is in the con of x k plus 1 up till x r, and x k plus 1 is in at least c1 c2 up till ck. X k plus 2 is in at least c1 c2 up till ck. X k plus 3 is in at least c1 c2 up till ck. So this is a subset of c1 intersection c2 which is a convex by this thing. So we proved that x star will then belong in c1, it will belong in c2, and all the way up to c2. So x star belongs in c1, x star belongs in c2, up to x star belongs in c2. And this completes the proof. We have shown that x star now belongs to each of these sets. Given experiment, we have shown that x star is in C1 intersection C2. Completing this. So Ellis Theorem is now complete. And it turns out that Ellis Theorem can be improved to arbitrarily large categories. So how does that work? That works under the assumption that you insist that each set is compact. So I am not going to prove that because that is just this argument plus some compactness argument. But I need to state it because it needs to get just used in Krasnoselskii's theorem. And for Krasnoselskii's theorem, I am going to do a little bit of hashing and a little bit of geometric vocabulary. Just going to jump around like a monkey. So I will be needing your patience for it. Very extended. Now you don't have some finite bunch of sets greater than n plus 2 or something. You have any bunch of uncountable perhaps sets. So you have Ci, I in I, convex, compact. Okay, and such that I has at least n plus 1 members. So it would have uncountably many, but at least n plus 1 it should have. Then Ellis conclusion. Then Ellis assumption. Implies Ellis conclusion. So if any of these b plus 1 subset, if any of these n plus 1 subsets are a non-empty intersection, then all of them, all uncountably many of them have an intersection. So you're taking uncountably many convex sets here, and I'm telling you there is a point that's sitting in all of them. That's incredible, right? So this, the proof is nothing but some Ellis normal plus compactness argument. What I'm going to put down is compactness argument. So I'm going to leave this as an exercise, or I'll even leave it as a black box. Okay? So plus compactness. Great. This result will be required to now prove the big one. And now let me tell you what Krasnoselskii's theorem is visually. You have a time for it before 35. What is visually Krasnoselskii's theorem? So Krasnoselskii's theorem is incredible because I'm going to cut out convex. Convex is gone. What we're going to do is we're going to use facts that use convexity very integrally to derive something for something which doesn't require compactness. So now let's assume that we just have a compact set. That's all. Compact set which is bounded close, nothing else. So it can be anything, some zero, right? It need not even be connected. So now the question is, this is an art gallery, okay, perhaps broken into parts. How and when can you say that one watchman is enough to supervise? So when is one watchman? Is one, literally one watchmen enough to supervise an art gallery. That's the question, right? And the theorem of Krasnoselskii says that if you can do it for any n plus 1 point, so let's say this art gallery is a subset of Rn, if any n plus 1 points can be supervised by one watchman, then in fact there is one watchman who can supervise everything. So basically speaking, Krasnoselskii is a sufficient condition for this one. So answer, not answer, partial, one of many answers is Krasnoselskii. Okay, now let me state. Keep the visibility thing in mind when you understand this. The reason why this theorem is so amazing is because of this entire art gallery connection. The fact that you can actually map it to having watchmen in an art gallery. And there is a more general research that goes into the art gallery thing. There are some theorems by T and Chopre and so on, but that is for a different day. Here. Okay, this is it. Let C subset of Rn be a compact set. That's all we need. Suppose for all choices of points x1, xn plus 1 in C, there is a watchman in C who can watch all of them, in the sense that the line segments joining y and x are contained entirely in C. Then there exists a single watchman located at a position x star such that for all y in C, x star y. Remarkable. What I told you is that every n plus 1 points being able to be watched by a single watchman implies that the entire art gallery can be watched by a single watchman. And now, what's the proof of this? Well, there are some technicalities in the proof. So, not really technicalities, I would say. The first part is pretty obvious. So, what you do is, you take, so let's say this is your compact set. Okay, this is your compact set. You take each point. No, sorry, I'm drawing the compact set as if it's convex. That's wrong. It can be any time compact set. Okay, let's just say it looks like this. Okay? You take each point and you find out how many guys are visible to you. You find out how many guys are visible to you. So, for example, this point is visible to this point, but this point is not visible to you. This point is not visible to you. So, you collect all such points. And then that collection, when ranged over every point in the compact set, you convexify each of them by taking the convex hull and apply Ellis. Uncountable. Okay. So now let me show you the rigorous one. Let x in C and Vx is equal to the set of all points visible from x. xy bar belongs. Okay? Sorry, not belongs in subset of C. So these are the V. The letter B is being used for the word visible. And what I will do is, as I said, I will convexify this. So V star x is equal to the smallest convex set containing x. Okay? And I can do this for all x and C. So this is a collection V star x, x in C, and can we apply Ellis theorem to this? Yes, because that's exactly what the hypothesis says. You see, what does the hypothesis say? The hypothesis says that if you take any points x1 up to xn plus 1, there is one point such that it's visible to each of them, right? So if y is such a point, then y is in Vx1, y is in Vx2 up till y being in Vxn plus 1. So y is in the intersection of each n plus 1 points, right? And once you convexify, it doesn't make a difference because the convex hull of Vx just contains Vx. So y is in Vx1 intersection up to Vxn plus 1 implies it will be in the convex hull, not a big deal. So Vx plus 1 satisfies Len's condition. So there is a point implies there is a point in x star that belongs in the intersection over x in C of con of Vx. Because we are still stuck with the Vx star. We've taken the convex hull so that we can use any, right? So it's in the intersection of the convex hulls of Vx. So now we make a stronger claim. X star is actually in intersection x in C Vx. So observe these two statements before that comes. One says that it's in the convex hull of each of the Vx. One says that it's in fact in each of the Vx. So this is just saying that it's the convex hull of the visible points. I'm literally telling you it's visible to every point. This is a claim. And if this is true, then x star is the point that we need, right? Then x star is the point that we need. Claim implies done. If you finish off this claim, we're done. Unfortunately, this claim, as a proof of it, is somewhat roundabout, to say the least. So I'm just going to be doing a little bit of hot geometry. If somebody doesn't understand this, don't worry, okay? But I'm just doing this for the sake of completeness. I don't want to be responsible. So, what I will do is, suppose it's not true. Suppose not. If this claim is not true, then that means there is a Vx to which x star doesn't belong, right? So, if not, then there exists y such that x star is in Vy, is not in Vy. Is not in Vy, right? So what that means is that when you're trying to view x star from y, you end up going outside the compact set. So for example, I erase this one. This is intentional. So let's say this is x. Oh sorry, this is x. Okay, it doesn't need to be complex, sorry. Right. So this is the point y, okay? The bad point, and this is the point x star, the optimal point, okay? Now what we're saying is that when we're trying to view x star from y, it's getting stuck. So we're ending up going outside the compact set C, which is here. So let u be any such point, right? So what we do is, we draw this line segment, and let u be a point on the line segment between x star and y such that u is not in C. Okay? So let u be this point. U is this point. Right? What I'm going to do now is, first I'll mark this point. I'm going to be completely non-rigorous, okay? So I'm not really going to expand and make be very detailed at this point. What we do is, we look at the first point where it exists. So this line segment is going out, right? Because u is on it. The first point where it exists, we call it x star. No, sorry, not call it x star. We'll call it x prime. We'll call it x prime. Now, what we do is, this point u is, we look at its distance from this convex at C. So say whatever the distance is, whatever this, right? we halve that distance. So we pick a point here W such that x star is the first exit point, and
X prime.
x prime. This is me getting confused with the text information. Anyway, x prime is the first exit point, and W, the distance between W and x prime, where W lies on this line segment, is exactly half the distance from U to any point on this compact set. So some say half d of U comma c. So d of U comma c literally means the shortest distance between U and this compact set. Okay? I'm just going to leave it to this. So d of W comma x bar, that's what that means. Now this line segment that you see here, WU, this is completely not contained in the convex set. It's literally outside. We've cut it off from this compact set. So now what we do is we find the 2 points on this compact set and this line that are closest to each other. So that's probably these 2 points. So this is a point, let's call it Z1, and this is a point, let's call it sorry? No, that distance is literally this distance. So the point is let me start again. Okay? X star is here, Y is here. Okay? X prime is the first exit. From Y, I start looking, and the first exit point from C is X prime. Okay? Now W is a point on this line segment on this side of X prime towards X star, such that the distance between W and X prime is half the distance between U and this set. So it's kind of cut off. We're kind of cutting it off. I told you, right? This proof is terribly random. And I didn't manage to improve it after an hour of working on it.
But it can also possibility the first diagram that this line might be again cutting the.
We're looking at the first cut point. This is a very simplified situation. This proof works in generality, but I'm just showing you a diagram just to convince you that one situation is there. But you can make all these rigors. I'm not planning them, not by a long distance, right? So what you do is you find the 2 closest points between the line segment and this. So that looks like Z1 and Z2, and you can show that this is a perpendicular. You can show that this is a perpendicular, and that if there is a supporting hyperplane here at Z2, you can show that even that is a perpendicular. It's literally like the supporting hyperplane at Z2 will be parallel to this. But anyway, that doesn't matter. Then what you do is you now, right? That's by assumption. X star definitely belongs in conv of Vz by assumption. So X star belongs in conv of Vz by assumption. Now what does that mean? That means that if you take the supporting hyperplane, now conv of Z2 is a convex set, and this is a supporting hyperplane for that convex set. So that convex set lies completely on this set. So this is that convex set, and it contains X star. So perhaps it's something like this, whatever it is. It's actually it should actually be contained inside C, but whatever. So it contains X star and this is a supporting hyperplane. Now look at this angle. This angle between X star, Z2 and Z1. What can you say about it? Angle between X star, Z2 and Z1. So if you have a plane here, this is a right angle, and there's a point here. This is Z2, this is Z1, and this is X star. This angle has to be an obtuse angle. This angle has to be greater than 90 degrees. And because this is greater than 90 degrees, this angle that you see here is smaller than 90 degrees. Right? This angle here is smaller than 90 degrees. So if you draw a triangle like Z2, Z1, X or whatever, then it's not apparent from this diagram, is it? But anyway, so if you look at that, this angle will be smaller than 90 degrees, and the contradiction here is very simple. You see, the contradiction here is that this was chosen to be the shortest distance. This was chosen to be the shortest distance. But now as I travel towards X, because I am traveling along an obtuse angle, there is eventually a point at which this should be 90 degrees. So this wouldn't have been 90 degrees in the first place. And that's the contradiction. So the point is, we chose Z1 and Z2 to minimize this distance, and because of this geometry over that we saw over here, it doesn't minimize that distance. So that actually creates a contradiction. and that's just a visual explanation of what happens. I have no earthly intention of writing down the details, but that then completes the proof. So this is just some kind of geometric generally that is just there. It's just there, and we have to do it as mathematicians. But then that will complete it. So the claim is complete and the proof. Any questions? That will complete my first lecture. Tomorrow's lecture will have a little bit of convex functions and probably a little bit of regularity. No questions for 2.5 hours off? Reference. Plenty of them, but some of them are new. From my previous math talk, I gave 55 of them. So one is A convex functions and their applications. Please don't read this one's proof. Krasnoselskii's proof. You will get confused by this entire machine. I just brought it to you because I needed to complete it. I could have actually perhaps I could have seen it. So what it is? Lay. Then there is a Nicolescu and Pearson's. Nicolescu and Pearson. Same thing. Convex functions in their application. The third book is a book by Boyd and Konzenberger. And this is called convex optimization. These three are pretty much where I picked up on PDF from. There is a fourth book, I think, it's by Krantz or something. Krantz. Geometry of convex domains. So geometry of convex domains is very interesting because what it starts taking the viewpoint immediately that we are chucking off geometrically convex, it introduces what are called as analytically convex sets, and then from analytically convex sets it's able to derive much more powerful theorems. Like duality and stuff is just a drop in the water for it. So it's able to derive far more important theorems. Like you cannot approach ED, for example, partial differential equations, without having regularity results out of convex domains. So that's just an example of why you require a more flexible definition for convex domain. And tomorrow when I discuss perhaps the support function, I'll come to that. Tomorrow's talk will be shorter. We have fewer explanations and a lot more